Okay, so the next thing we're going to talk about here are how we can represent a graph on a computer, for example. How we can represent a graph. Now, I'm not going to talk about every way you can do this. There's many such ways of doing them. Some of these aren't even all of them that are out there. I'm going to show you a couple. So I'm going to talk about them in the context of two things. First, I'm going to give you a classic representation. Then I'm also going to give you more of an object-oriented generalized representation. So the reason why I do this is so that you can get an intuition behind what all you need to really represent the graph, versus if you want to add more stuff to represent your graph or adapt your graph to have more of an object-oriented approach to it. Say the vertices represent actual things and you want to have actual parameters or other attributes they may have. This generalized approach is just a simple extension on it. So if you're using an object-oriented programming language, you could pick it up and say, hey, I want this object, this object, this object. How do I represent that with the graph? That's what I want to address. So if you want to just start off with just something as simple as just using arrays or two-dimensional arrays or linked lists, you'll see that all of these elementary representations are easy enough to get a graph. So the first type is the adjacency matrix that I'll talk about here. So adjacency matrix. As the name suggests, it's based on the adjacent relationships between vertices or nodes. So the relationships that are going to be captured are based on adjacency. So what do I mean by this? You can think of it as something as a matrix, which either is a table or a two-dimensional array. It stores zeros and ones, or as I'm going to show you, you can go a little further with this if you like. Zeros and ones, where if I give you a 2D array, Aij, we would say it's 1 in the spot or 0 in the spot. If it's 1, then that means that the edge ij is in the set of edges. 0 if ij is not in the set of edges. So that means that if there's a 1 in this spot in the matrix, that means that that edge exists in the graph. If it's a 0, it is not. So let me do an example here for you. So let's do an example. So suppose I have this matrix, this graph. I'm just going to label all the edges just to help us see what we can do here. So I'm going to V0, V4, V3, V1, and V2. So I'm going to call this one D, going to call that E, going to call this C. I think I've labeled all the edges and vertices. So if we take a look at this, what I'm going to do is I'm going to presume with this representation that vertices are labeled 0 through n-1 if there's n vertices. So it means that in our rows and columns, they'll start off at 0, 0, 1, 2, 3, 4. So there's 5 vertices here, so it starts 0, 1, 2, 3, 4. 0 is for V0, 1 is for V1, 2 is for V2, 3 is for V3, 4 is for V4. Okay? And then naturally, each one of these may be adjacent to another vertex, each respectively labeled as 0 through 4. And now you might ask, Dan, why are you labeling them at 0 through 4? It's because even though you could give these names, like specialized labels, or they may have associated objects with them, you could look at these also as indices, ways you can index into the table, or two-dimensional array, matrix, however you'd like to look at it. So for example, if I look at this graph here, do I see an edge from V0 to V0? No. In fact, you could do this with every one of the vertices here. None of them have self loops. So you know right away the diagonal of this matrix has zeros in it. Now, V0 is not adjacent to V1, so you know it's not there. You can also, by the way, you could also notice that V1 isn't adjacent to V0, so I'm gonna just put 0 there too. Okay, V2, now V0 is not adjacent to V2. It's only adjacent to V4, so you know there's just gonna be a 1 there. Now next, let's look at V1. V1 is adjacent to V2 and V3. So we have V2, V3. It's not adjacent to V4 though, right? Now, vertex 2. Vertex 2 is adjacent to V1 and V3 of vertex 1, vertex 3. Vertex 1, vertex 3. But it's not adjacent to anything else. Does everybody see that? So now, we've got V3. V3 is adjacent to V2, V1, and V4. V2, V1, V4. It's not adjacent to V... Well, let's think about this. V3... It's not adjacent to V0, sorry. Yes. Now, next, we have V4. V4, let's take a look. Well, V4 is adjacent to V0, but it's not adjacent to V1, V2. It's only adjacent to V3. And there's our adjacency matrix. So this matrix tells you if a vertex is adjacent to another vertex. So you can use this information to represent a graph. Because remember, like I told you at the beginning of our lesson, it's fundamentally about the representation of the connections between vertices that really matter here. I must stress that this representation is very easy to augment too. So for example, if you want to have distances, you replace the ones with distances and make everything else like infinity or something. I'll have more discussion about that if we talk about where or if we need what we call weighted graphs. I'll talk about that. So one other thing, I promised you I was going to show you how you can generalize this idea. So what you do is here's like a very object-oriented way you can look at this way of doing things. So what you could do is you still have a two-dimensional array. You still have it where you're indexing like this, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. And now instead of storing zeros, you store null pointers or nil or null, whatever language you would have for whatever the conception of null might be. It might be 0, literally. So suppose all of these are nulls. So wherever I had a 0 there, I'm going to make that null. So I have null, 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 null. And wherever I don't have a null, I'm going to put I would have a pointer or a reference to the edge object that's associating the two vertices. So what I would do here is if I have my edges, which I've labeled here, suppose that each of these is an edge object. So I want to have an actual object for the edges. I can index into a spot to get that edge object. So for example here, V0, V4, there's A, right? So you could just have a reference or pointer to A. So if ever you need to do anything with the graph, like say these edges represent something for you, you can use it this way. Likewise, you can even have an array just for your vertex objects as well. So if ever you need to do things like marking them or tweaking some input they may have or attribute. Let me complete this for you. So we would have D, then E, then another null, then you would have D, then you would have, I believe, another null. I guess the whole diagonal would have nulls, right? Because they all have zeros. So you'd have E here, you'd have C, C. By the way I'm filling this in, do you see anything interesting going on with that matrix over there if you've learned a bit about matrices? N, I have a B, I have a B, I have an N, and an N. Is there anything interesting going on here, by the way? Did you see anything interesting going on? What I wanted you to do is look at the diagonal here. So start by looking at the upper triangle, so this side of the matrix. Do you see anything interesting going on with the opposing side? It's like a mirror image of it. So you just take this, go like that, they're the same. Just a mirror of it. You do the same thing with this matrix. With an undirected graph, this matrix will always be what we call symmetric. That means the upper triangle is going to be, in the lower triangle, they're going to match each other like this. In a directed graph, that isn't true though. But like I said, you could represent a directed graph using the same approach as well. Just the matrix won't necessarily be symmetric like this. It's a nice property that also, if ever you care to optimize this representation, you could just simply get rid of the lower triangle if you're trying to optimize, but you have to keep in mind that now then you'll have to make sure you take into account that you have the ordering of the vertices correctly whenever you're indexing into this. So just one other thing you can keep in mind, but you can still use this space. It's probably useful just to use the space if you have it. But that's just the other point of discussion. One thing I want to bring up about this representation, so if you know how to make a 2D array, you know how to represent a graph. Piece of cake, right? So space, this uses big O of n squared space. So notice that the dimensions of this table or matrix or 2D array, it's n by n. So notice that you're going to have big O of n squared space, presuming everything that's being stored in these is some constant amount of space that's being used. So that's one thing you have to keep in mind. So this is appropriate heavily for graphs that are dense, meaning they have many edges in them. So this is, I'll use good in quotation marks. I don't really like talking about good and bad and this kind of stuff. It's more of a trade-off game. It's about pros and cons. So if the graph is dense, meaning it has many edges in it, which this should remind you of something that we talked about earlier on. Do you remember me telling you about the maximum number of edges a simple graph could have? It's the same as this. So the closer your graph becomes to a complete graph, the better this representation will be utilized. Because then notice that if you don't have a dense graph, many of these are going to be zero. And it means you're just wasting space, probably. We really care about the ones. The ones are what really matter. So sometimes even people will optimize this representation into something called a sparse matrix, where you turn this more into a linked-based structure. But I won't talk about that here. The big perk of the adjacency matrix is that if you ever want to check if an edge ij is in the graph, how do you do that? How do you do that? What do you do? You just simply index into the two respective spots, right? If I want to know if vertex, if I want to know there is an edge whose endpoints are I and j, I just look at the matrix, right? So if I want to look for, say, 0, 4, if there's an edge, 0, 4. I go into row 0, go column 4, it's right there, there's a 1. So I know that there is an edge there. In fact, if I use this representation, I can literally get the edge object. But I could do this in big O of 1 time, in constant time. It's very fast. One remark I also want to make, if you're curious about, okay, Dan, I don't really, suppose I have a bunch of objects that actually are trying to access parts of this graph. Well, you can always use a lookup table that will tell you what their number is in here, what some people call a map. And that's a whole other topic for its own right that I do talk about in some of my data structures videos. So these are a couple things to keep in mind when it comes to this. One other detail I really want you to be aware of is if ever you need to get all of the edges that are incident on a vertex, you're going to require big O of n time. You're going to take linear time to do this because you have to access one row of this matrix. You have to read through it. Sometimes there's zeros, sometimes there's ones. To collect those up, you need to go through one of the rows of this matrix. So please keep that in mind. It's actually rather important for the analysis if ever decide you want to use one of these. so that's the adjacency matrix. Piece of cake, right? So the next representation we're going to talk about is the adjacency list. And it attempts to address one of the major issues that we had here. But anyways, the next representation we're going to talk about is the adjacency list. Now, the main objective here with the adjacency list is to address this issue that we had over here. So notice that I had a lot of I could potentially have a lot of zeros if my graph is what we call sparse. So meaning that the number of edges is more like big O of n as opposed to big O of n squared. Meaning it's more of a linear number. So it's kind of relative to the number of vertices-ish. It can be off by constant magnitudes, but it won't be. The point is that there might not be as many edges. There's less edges than there are for a really dense graph. So what we're going to have is what we call an incident sequence. So some people would even call this a collection of incident edges. So in the most purest sense, you'll see that this actually gives you the information about incidents, just akin to whenever I wanted to get the incident edges over there. So it's going to have an incident sequence for each vertex. Where there is a collection of incident edges for vertex V. So for each one of the vertices, you're going to have a collection of incident edges, which in the adjacency list in its most pure sense will just store all of the adjacent vertices. But very often you'll find that this is actually, well, I mean, it gives you the information as well about incident edges too, which is nice. But you can also have this storing the information of each vertex or the edge objects if you ever need edge objects. So like that, you can also generalize it. So classically, you got to look at it like this. So what I'm going to do is I'm going to use the same graph I had over there, just for the sake of consistency. So I'm going to have V0, V4, V3, V1, and V2. So I'm going to have D, E, C, B, and A. And classically, you'll find that this is represented as follows. 0, 1, 2, 3, 4. What's going to happen is we're going to have an array or a list that is going to contain pointers or references to linked lists. So each one of these is actually going to be the head of a linked list. Each will store the opposing endpoint of each incident edge. So for example, if I look at vertex 0 over here, well, look, there is 4 is one of its neighbors. It's one of the adjacent vertices to V0. Likewise, if I look at V1, notice it's 2 and 3. Likewise, I look at vertex 2, which just has vertex 1 and vertex 3. And naturally, you could keep doing this. So 3, well, if I look at vertex 3, I have 1, vertex 1, vertex 2, and vertex 4. And vertex 4 has 0 and 3. Do you see all I have is just an array or list. Each one stores the head of a linked list. That's all it does. So you can look at the storage of this as just an array of length n each one with a linked list. So just please keep that in mind. Naturally, you can extend this into a primary data structure that is going to be a list or some data structure that's going to allow you to index in like this, similar to a map. And for each one of those, we'll have a secondary data structure, which could be some collection of incident edges. So this could be a secondary data structure of your choice. So usually, classically, it's just a linked list because specializing it requires you to have more information. This is easy enough to do, but you can always have it where it's a primary structure, where it's like some map, and then you have it where each one of these, once you have the index to get in, you can get the incident edges. And the incident edges are stored in some collection. So that's the adjacency list. It's surprisingly simple as well, as long as you understand that over there you're dealing with a two-dimensional array, here you're dealing with an array, and then you're dealing with each one of these having a linked list. If you know how to implement a 2D array and implement a linked list, you can implement any one of these graphs. Piece of cake, right? So two things I wanted to mention. So the first thing is that we always have these sort of drawbacks to each one. But I really want to point out something that's rather important here. And this actually comes back to our best friend, the handshaking lemma. So how much space does an adjacency list use? Well, it has a reference or pointer for each one of the vertices, right? So you know the amount of space it's going to use is at least n. But what's the length of each one of these linked lists? How many nodes are in each one of these linked lists? I would like to know the answer to this. See, this is where this handshaking lemma is going to be your best friend. So notice, because it's an adjacency list, if you look at our definition here, it's an incident sequence for each vertex. So if you look at each one of our linked lists, how many nodes will there be in each linked list? The degree. So notice that the degree, so each one of these, so each list has the degree of some vertex. So like say degree of vi, many nodes. But what is that if I add up all of these? That's the sum of the degrees, right? Over all the vertices. And as we established by the handshaking lemma, this is exactly equal to 2 times m, which this is big O of m. Because it's just 2 times m. M is 2 is a constant. So now the total amount of space to represent this is this array and all of these nodes, presuming that each one of these objects is big O of 1 in its space. So this has a benefit if the m is not close to big O of n squared, right? Otherwise it just devolves into big O of n squared like we have over there. But either way, these two representations will allow you to represent any one graph. So this is one big perk this has. If you have a sparse graph, so one that is close to big O of n in its edges or very few edges, this is substantially better in storage than the adjacency matrix is, right? However, it requires a little bit more work for its implementation. The adjacency matrix is much simpler to implement. So that's the first thing. Now, so that's the good news I have for you. Now, if ever I want to find out if a vertex is adjacent to another vertex, well, let's answer that question. How do we know? Like, suppose I want to know if vertex 1 is adjacent to vertex 3. Well, I would have to index into this spot, which this is just an array. I'm going to use the number that corresponds to that vertex to get here. And then I have to navigate this linked list, right? Well, suppose that I access vertex 3 or vertex 1. Either one should be able to tell me, because it's an undirected graph, it doesn't matter which one I use. If I go vertex 1, it'll be able to tell me vertex 3 is adjacent to it by traversing this linked list. But how long can this list be? Well, it's based on the degree of the vertex, right? So if it's a directed graph, you would have to index into the first endpoint to get to the second one. If it exists, it'll tell you yes or no if you traverse through here. Okay? You just go through one by one, traversing a linked list. If you know how to do that, you know how to test for adjacency. So this is going to take... So it's going to be big O of either the sum of the degrees, or more simply, it could just simply be you pick, because all you have to do is you pick one of the two. So it's going to be so it could be the sum of these, it could be the min of the two, it could be the... Keep in mind, you can always have it where you tweak this a little bit. So you could say, okay, well, which one's the shorter of the two? I'll take the shorter of the two. But because keep in mind, if I do access this spot and it's indeed adjacent to the other endpoint, it doesn't matter which of the two you go down. But the point is it depends on the degree of the vertex. That's the point. And the degree, if this is, say, a complete graph, you may have to take, it may take linear time in the worst case. Because what's the degree of any vertex in a complete graph? It's big O of n, because it's n minus 1. So one thing I wanted to bring up for you, just to kind of cap off this discussion, is why would we care about if a graph is dense, like a complete graph, or sparse, like where it has very few edges, or not as many edges. It's not close to big O of n squared. I thought I would give you an example of a graph that is sparse, and it does occur itself in many applications. There's many kinds of graphs like these. So knowing about the structure of the graph, how many edges does it have? The underlying topology of the graph, like what structure does it have? These are all very important things to investigate if you have a graph that you're using for some application. So I thought I'd give you an example. So the big thing to take away from an adjacency list is if M is big O of n, then this will be quite efficient. Because many of the operations, otherwise it sort of, the edges, because there's so it can have so many of them, it could be the case that this actually starts just becoming no different than what we were dealing with when we started, right? So I thought I'd give you an example of a sparse graph. So something called a planar graph. So this is a graph where there exists a way to embed or draw it in the plane. So when I'm talking about the plane, I'm like talking like a piece of paper like this. So you could draw it on the piece of paper. In the plane. So I'm not talking about like a literal airplane or something. Think of this like a piece of paper. I want to draw it here. Such that its edges only cross at their endpoints, so at the vertices. So believe it or not, a lot of different kinds of graphs you encounter in practice actually are this. So I'll give you an example. Actually, I alluded to this one previously. So suppose I give you K4. So here's K4. So here's one possible way I could draw K4 for you. Now, You might say, Dan, does this have any crossings in it? And the answer is yes, it does. It has one, at least one. It's right here. There's a crossing right here. But if you read my definition here very carefully, that doesn't preclude it from being a planar graph. So this is a graph where there exists. That means there's at least one way to embed or draw it in the plane such that its edges only cross at their endpoints, right? Well, that's not a good drawing of this. If you look at this a little more carefully, take this vertex, drag it inside of the triangle like this, and you end up with another drawing I showed you in the past. And this is the same graph. So there's no crossing. This is still K4. So that means that this graph is planar. So K4 is planar. So graphs that are planar actually have very few edges in them. So, for example, we've talked about trees. We know trees have n-1 edges in them, right? So that means that the number of edges is big O of n. There's all sorts of other ones that have very few edges in them. Planar graphs are one of them. So if you encounter a planar graph, the adjacency list representation will be your best friend, because planar graphs also have this property. So if you're wondering where you might run into things like this, if you're dealing with geographical information that's on a flat surface, now keep in mind, real world geography is not flat, right? However, if you're dealing with a simple model where I want to go from A to B, and you want to go there and you have estimates of how long it might take, a lot of that information, presuming that you're not dealing with any weird structural properties that you may have with a highway or anything like that. If you're just dealing with simple little intersections at roads, it's probably planar. So keep that in mind. There's a lot of applications out there for design of circuit boards and all these other things that involve planar graphs.